Section 11.3.3-T. Use the given statistics to complete parts A and B, assuming that the populations are normally distributed. We have population 1, population 2. Here's the sample sizes, sample mean, and the sample standard deviation. In part A, we want to test whether population mean 1 is greater than population mean 2 at the significance level of 0.10 for the given sample data. So, since we already know that the populations are normally distributed, we can go ahead and start writing out our null and our alternative hypothesis. Well, the claim is to test whether population mean 1 is greater than population mean 2, so now we know what the alternative is going to be. And therefore, the null is going to have the equality. Okay, step 2. What kind of test is this? Well, since it's a greater than, we know it's going to be a right tail test. And number 3, we know that we're testing it at the significance level of 0.10. Okay, now for step 4, what we want to be able to do is we want to be able to figure out what is the test statistic. So we know the information that we have from the particular problem here. We know that we have the following. We know that sample size 1, there's N1, we have mean 1, which is the following, and then we have the standard deviation. And then we have the sample size, which is 24, the mean there, and then the standard deviation. Okay, and then what else do we need to know? Well, we know the following. We know that mu1 is equal to mu2, and if we wanted to subtract mu2 to both sides, then that means it's going to equal 0. So now we can go ahead and find out what the test statistic is going to be. So we know that mean 1 is 49.5 minus sample mean 2, which is 46.0, and it's minus 0 since mu1 minus mu2 is equal to 0. And then we're going to take the standard deviation of sample 1, which is 6.3. We're going to square it and then divide it by the sample size of 27, plus the standard deviation of population 2, which is 10.1. We're going to square that and divide it by the sample size, which is 24. Okay, now let's go ahead and see what this looks like on our calculator. Okay, so in the numerator we have 49.5 minus 46, and that's minus 0, so therefore we know that we have 3.5 in the numerator. We're going to select divide, and then second square root. We're going to put parentheses around the first part, so we have parentheses 6.3 squared divided by 27, parentheses, and then plus parentheses again, 10.1 squared, and then we're dividing that by 24, close the parentheses, hit the arrow key, and therefore we get the following. So let's go ahead and copy that. So we're going to round that to 2 decimal places. And so rounding that to 2 decimal places is going to give us 1.46 for the test statistic. Okay, so now what we're going to do is we're going to be able to draw bell curve with the test statistic so that we can figure out how to find the p-value. So here we have our bell curve. We know that we have the mean of 0. We know that our test statistic is located at 1.46. And then what we want to be able to find is we want to find the p-value that's located here. Okay. Now there's two ways to find the p-value. Okay, now MyMathLab will take two different particular answers, and I want to show you so that you can see the differences between the two. Okay, the first is using the degrees of freedom formula here. So if we wanted to use this formula, then what that means is we're going to take the standard deviation for sample 1, which is 6.3, square it, and then divide it by the sample size of 27, plus standard deviation of 10.1, squaring it and divided by the sample size of 24. And then we're going to divide that by, again, the standard deviation, which is 6.3 squared over 27 squared. And that's going to be over the sample size, which is 27 minus 1, which is then going to be 26. And then plus, we have 10.1 squared over the sample size of 24, squaring that all over, in this case here, 24 minus 1, which is going to be 23. Okay, so this is going to give us the degrees of freedom. And so just to have a quick review of how to go about the calculator version, we're going to first evaluate the numerator and then evaluate the denominator by using order of operations. So we know that we have 6.3, and that should be squared here. Okay, so we have 6.3 squared, and then we're going to divide that by 27. That's the first part. And then we're going to add 10.1 squared, and we're dividing that by 24. Now we need to take that value and then square it. So we're going to take second answer and we're going to square that, and that's going to give us the numerator. So I'm just going to go ahead and write that as the numerator. Okay, and then we're going to divide it by the denominator. And so let's go ahead and evaluate the denominator. We have 6.3 squared divided by 27. And then we're going to square that number and then divide that by 26. And then we're going to add, okay, and now we're going to do this all in one order of operations. Okay, we're going to take parentheses 10.1 squared divided by 24 parentheses squared, and then divide that by 23, and then that's going to give us that number. Okay, and then rather than writing these numbers again, when you're using the TI-84, we can come back up here and then hit enter for this last number that we found. So if you hit enter, and then divide it by the last answer, meaning divide by the second answer, it's going to give us the degrees of freedom here. And here we have the degrees of freedom for the following. Okay, so the reason I want to show you this is because if you're using StatCrunch or the calculator version, this is the degrees of freedom that it's going to give you. Otherwise, we would then choose the smaller of the sample size and then take the degrees of freedom there. So at this point here, we can find two different p-values that'll give us the answer when we're putting them in. So if we're using the p-value, I'm going to have two different p-values here. Okay, the first p-value, we're going to use TCDF. We know that our lower limit is 1.46. We know that our upper limit is 9999. And then we have our degrees of freedom, which is 37.6. So let's go ahead and find the p-value. So if we take second distribution, scroll down to TCDF, we know that our lower limit is 1.46. We know that we have 9999. And then let's go ahead and just put this number in. We got 37.67 for our degrees of freedom, and then select paste. And then it's going to give us this value for our p-value. Okay, and then we would round that to 3 decimal places, which then gives us 0.076. Okay, now it's also in the book, it tells us that we can take the p-value by doing the following. So we can still do the same thing. We can say TCDF, use the lower limit of 1.46, an upper limit of 9999. And then the smaller of the sample size is 24. So we can use the degrees of freedom here to be 24 minus 1, which is going to give us 23. So let's go ahead and find out what that number would then look like. Okay, so if we take TCDF, and then in this case here, we're going to go ahead and then put in the degrees of freedom to be 23, and then select enter, we're going to get the following p-value. Okay, now, again, when you're looking at this p-value, using the calculator in this form, using the degrees of freedom of 23, it gives us something close to that, but not exact. So when we want to find the p-value there, this is going to be 0.079, okay? So you can see how close it is, right? But when you put this into my math lab, either or is going to be correct because it gives you correct to a certain amount of decimal points. So if you're using the smaller of the degrees of freedom, it's going to be okay. Or you can use the actual formula to find the degrees of freedom. Okay? Okay, now that we found the p-value, we want to be able to now compare it with the significance level. Okay, so remember that if the p-value is less than alpha, then reject the null hypothesis. Otherwise, do not reject the null hypothesis. Well, let's take a look at what the p-value is. Well, the p-value that we found versus alpha. Well, the p-value, we'll use the 0.076, and we know that the significance level is 0.10. And so therefore, this is less than. And since it's less than, we're going to reject the null hypothesis. So therefore, we can then write the conclusion and then state the following. Reject the null hypothesis, and then we would say that there is sufficient evidence at the alpha equals 0.10 level of significance to conclude that population mean 1 is greater than population mean 2. Okay, let's move into part B and then find the 95% confidence interval. Okay, so we need the formula for the upper bound and the lower bound. So we need that. So here's our formula for the lower bound and the upper bound. And then let's go ahead and just copy down the data up here so we know what we need to plug in. Okay, so we know what population mean and sample size, standard deviation for 1 and 2 is. Okay, just like we did up here, we found a p-value for when we use the degrees of freedom for 23. And we also found a p-value when the degrees of freedom was 37. Okay, or we can round that up and use it as 38. So let's first use the degrees of freedom. Okay, so in order to find the lower bound and the upper bound, we already have our mean and we have our standard deviation and our sample size. And now what we want to do is we want to find our critical value. So we're going to find our critical value for when we use the smaller of the sample size minus 1, or we can use this degrees of freedom that we already found. So let's look at both. So up here, the degrees of freedom that we found using the formula was 37.6. We're going to round down to 37. So if we take alpha and take 1 minus 0.95, that gives us 0.05. And we're going to take alpha and divide that by 2, which is 0.05 divided by 2, which gives us the area in the right tail to be 0.025. And then using the degrees of freedom of the formula that we used, we round that down to 37. So let's take a look at our t-distribution to find out what that critical value is going to be. So we have the area of 0.025. We know our degrees of freedom is 37. So it's going to give us a critical value of 2.026. So the critical t value is 2.026. Okay, now let's use the formula here. So we're going to take our mean to find the lower bound. So mean of population 1, which is 49.5, minus the mean 46.0, minus the critical value of 2.026, times the square root of the standard deviation, 6.3 squared, divided by the population size of 27, plus the standard deviation of 10.1 squared, divided by 24. Okay, so let's go ahead and plug that into our calculator. So we have 6.3 squared divided by 27 plus 10.1 squared divided by 24. So we worked inside the radical. Now we're going to take the square root of that number. So the second square root of second answer. And therefore there's that value. And now we're going to multiply that by negative 2.026, which is this number here. And then we're going to add parentheses 49.5 minus 46.0. And there is our number. So let's go ahead and copy that number here. So we have negative 1.35663732. Okay, and then let's round that to 3 decimal places. So if we round that to 3 decimal places, then we have negative 1.346. Okay, now let's find the upper bound. So basically what we're going to do now is just add the right part of this. So we're going to go ahead and do the following. So by looking for the upper bound, you're now going to add the critical value times what we have there. So let's go ahead and open this up. So you can see here that when we take the square root of that result of what's inside here, we end up getting this number. So let's press enter, and then we're going to multiply it by the critical value of 2.026. And then we're going to add, we get 49.5 minus 46. And that gives us the following result. So rounding that to 3 decimal places, then we get 8.346. So then we would say that the interval, or the 95% confidence interval, is going to start from negative 1.346 to 8.346. Okay, so we can go ahead and then conclude that the following. We would say that there is a 95% confidence interval about population mean 1 minus population mean 2 is the range from a lower bound of negative 1.346 to an upper bound of 8.346. Now again, that's because we use the critical value using a degrees of freedom for 37 to be 2.026. Now, if we use the calculator version or StatCrunch, our decimal might be a little bit off in the hundreds place. Okay, so what I mean by that is, okay, let's go ahead and take a look at what it would look like using a TI-80 for test. So we're going to go to Stat. We're going to scroll to the right where it says Tests. And then we're going to go all the way down to where we see the 2 sample t interval. Okay, and then if we put in the stats, we put in the mean, the standard deviation, the sample size, and then again, the information for population 2 with a confidence level of 0.95, and it's pulled as no, and then select enter. Okay, you're going to see that we're going to get a confidence interval that says negative 1.343, which is a little bit different than what we get there. Because again, we're rounding down with the degrees of freedom that we have, which is what we got over here. So when you're using a calculator or StatCrunch, the number may be a little bit off depending on using that form. Okay, and then in addition to that, okay, now according to the instructions, since we used the degrees of freedom that we did for 37, now if we used the degrees of freedom to be 23, then if you see here, we're going to get a different critical t value. Okay, and how do we get that critical t value? We just do the same thing that we did over here. The only thing is that the area is still going to be the same, okay, which is 0.025, but then we're using the degrees of freedom of 23. So we would see here that we would get then the critical value to be 2.069, and so therefore that would be 2.069, and then all the other information would stay the same. So when we round it to 3 decimal places, you can see that our numbers are just slightly off here a little bit more because it's negative 1.449 and 8.449. So again, it'll take the answers. It just depends on which degrees of freedom that you're going to use.